Sophie and you're watching Science of It. Today we're going to be looking at all things circular motion. So let's get going. If you've done any physics before, you've probably looked at linear motion, and you'll be glad to know that circular motion is quite similar. So for linear motion, you've got the equations of motion, or the SUVAT equations, which are s equals ut plus a half at squared, v squared equals u squared plus 2as, and a equals v minus u over t. And for circular motion, it's basically the same, well, it is exactly the same, but just with different symbols that have different meanings. So we're going to go through these meanings, and hopefully that'll help you to start to get to grips with circular motion. So to get from linear motion to circular motion, we know that each element of the linear motion equations has an angular equivalent. Acceleration, a, goes to alpha, which is measured in radians per second squared. Initial linear speed, or u, goes to omega naught, which is measured in radians per second. And similarly, final linear speed goes to omega, which is also measured in radians per second. Then we have distance, which is measured in meters for linear distance, and this goes to theta, which is measured in radians. You can't really say there's a linear and angular time, so time just stays exactly the same. So on the left we have our linear equations of motion, or our SUVAT equations, and all you have to do to get to our equations of circular motion is sub in the angular equivalents that we saw before. And that's all there is to it. The one most important thing, the thing that makes circular motion happen, is a centripetal force, or centripetal acceleration. So you can calculate the centripetal force using mv squared over r, and it's always directed towards the center of the circle, or the curve that you're moving in. It's similar to force equals mass times acceleration, so acceleration in this case would be v squared over r, and that is the centripetal acceleration. And then you just multiply that by the mass, and that gives you the centripetal force. The equation for centripetal force can also be written in angular terms. So mv squared over r is the same as saying m omega squared r, and this is because omega equals v over r. The centripetal force is supplied by different things in different situations. So for example, if you're in a car and you're going round and roundabout, then the centripetal force will be provided by the friction between the car's tires and the road surface. This can be a little bit hard to get your head around, so let's go through an example to try and explain that a bit better. Okay, a ball on a string is attached to a fixed point and is moving in a horizontal circle at a constant speed of 8.8 meters per second. The radius of the circle is 7.6 meters, and the ball has a mass of 380 kilograms. Calculate the centripetal force acting on the ball. So the first thing I would do is pick out the values we're given in the question. So v equals 8.8, r equals 7.6, and m equals 380. Next, we have to state the equation for the centripetal force, which in this case the best one to use would be mv squared over r, and then you just sub in the values that you're given in the question. And following this through, we get 3,900 newtons. The next part of the question asks us to state the direction of the centripetal force. In questions like these, it can be useful to think about all of the different forces acting on the system. So first we have the tension, which is acting along the length of the string, and we also have the weight of the ball, which is acting downwards. We can resolve the force of tension into its horizontal and vertical components using trig. The vertical component would be t cos theta, and the horizontal component would be t sine theta, as sine theta equals opposite over hypotenuse, and cos theta equals adjacent over hypotenuse. We know that the centripetal force always acts towards the centre of the circle, and in this case we can say that the centripetal force is provided by the horizontal component of the tension, which is T equals sine theta. Next, we're asked to find an expression for the tension in the string. So, resolving the forces vertically, we have T cos theta equals mg, which is the weight. And rearranging, this gives us T equals mg over cos theta. Find an expression for the linear speed of the ball. So, looking at the horizontal forces, we can say that the centripetal force equals T sine theta, as we found out before. So this means that mv squared over r equals T sine theta. Now we can sub in the expression that we found for the tension and cancel the mass on either side. This gives us v squared over r equals g tan theta, as sine theta over cos theta equals tan theta. Rearranging, this gives us an expression for the linear speed as root gr tan theta meters per second. So for the last part, the speed of the ball decreases. What effect does this have on angle theta? So we know that if the linear speed is decreasing, then the centripetal force also has to decrease. Looking at our working from before, since the weight force stays constant, we can see that as v squared over r decreases, then g tan theta must also decrease, and since g is a constant, this means tan theta itself has to decrease. So that means that the angle theta also decreases. Thanks for watching. Hope you found this useful, and good luck in advanced higher physics if you're taking the course. Next time we'll continue going through the kinematics topics, and yeah, I hope this has been helpful. See you in the next one. Centripetal force, or centripetal force, centripetal